All right. So it's my great pleasure to introduce the next AMS invited address of this meeting. And so the speaker is Semyon Dyatlov of MIT. And just a brief bio, he got his undergraduate education in Novosibirsk in Siberia. And then he came to Berkeley, where he received his PhD under my largely nominal supervision in 2013. And got a Clay Fellowship, moved to MIT, came back to Berkeley, eventually went back to MIT, where he's now a full professor. He got the International Association of Mathematical Physics Early Career Award. AMS and EMS recognized his work with the Mikhail Gorin Prize, and he was also an ICM speaker 3 years ago. So it is my great pleasure to introduce the talk on uncertainty principles in quantum chaos by Semyon Dyatlov. Professor Dyatlov.
Yeah. Thank you, Maciej, and I would like to thank the AMS and the organizers of the. Can you hear me? Okay. Thank you, Maciej, and I would like to thank the AMS and the organizers of the joint mathematics meetings for giving me an opportunity to speak here. So let me jump right into what I'm going to be talking about today. And this is high energy behavior of Laplace eigenfunctions. So let me first give the mathematical definitions. I'll start with the simplest setting. It's not necessarily simplest to study, but it's the simplest one to formulate, which is a bounded planar domain. Nice, smooth boundary in R2. And then it is well known that if you put some boundary conditions, here let's take Dirichlet boundary conditions, you have a complete system of eigenfunctions of the Laplace operator. That's one of the kind of fundamental old theorems in PDE, and then you can use these eigenfunctions for many reasons. You can use them to solve the wave equation, the heat equation, Schrödinger equation, but in general, they are this fundamental basis of L2 of your domain, which tells you a lot of interesting spectral information about it. Okay, so I'll call my eigenvalue lambda j squared, and the eigenvalue will go to infinity, and I will normalize them to be 1 in L2, so square integral. So the interpretation I'll take today is a quantum mechanical interpretation. Imagine that you somehow managed to perfectly trap a quantum particle in this domain. Never exactly possible. The world is not as easy. But imagine you had a quantum particle was perfectly constrained to domain. Then these UJs will be known as the wave functions of pure quantum states of this particle. And then absolute value UJ squared dx is a probability measure due to the normalization. And the common interpretation in quantum mechanics is that this is the probability distribution of the location of your particle. So that's a good way to think about it in the context of today's talk. All right. So let me specialize a bit more. I will only care about the behavior of those eigenfunctions in the high energy limit. So my eigenvalue will go to infinity, and then I want to know what does my eigenfunction do. In a moment, you will see that you cannot have a strong limit of those eigenfunctions. They will start oscillating a lot. But what you can do is you can study macroscopic behavior. And you can study this absolute value j squared dx as a probability measure. So one property that I'm in particular interested in is equidistribution. So this is, in terms of probability, it means the weak limit of this measure is the volume measure. But let me define it here. So for any classical observable, or for any test function, which is a continuous function in your domain, if I integrate it against absolute value j squared dx, the limit should be just the integral of a dx. So this means that in the high frequency limit, the probability of finding your quantum particle in a fixed macroscopic set, so the set cannot depend on lambda j, becomes proportional to the volume of that set. So it's equidistributed according to volume. OK. So that's the kind of property that I will be interested in. And well, let's look at some plots. I'll try to alternate things with pictures. The talk will get more dense as we progress, but I'll start with just 2 pictures. Here are 2 domains, a disk and a stadium. And here are 2 typical high-energy eigenfunctions. The one on the right is due to Alex Barnett. The one on the left, not hard to plot. I could do it myself. Yeah, so you see that for the disk, you have no equidistribution. For example, you have a white hole in the middle. Right, so what's plotted here is absolute value uj squared. So you just numerically compute these eigenfunctions, and you plot absolute value j squared. Black is bigger. White is smaller. So white is 0, and black is bigger. So on the right, you see that you have equidistribution. Of course, you see a lot of interesting features. You see, for example, this kind of stuff, and you have all these pictures of eigenfunctions. But if I think about it macroscopically, like I zoom out, or I'm not wearing glasses, but imagine I took off my contacts, which I'm not going to do for you now, but just imagine, and I look at it from a distance, it just looks all gray uniformly. And that's this kind of macroscopic limit equidistribution property. So what's so different between those 2 domains? Well, the classical difference is actually the long-time behavior of billiard trajectories. And so it turns out that this is the geometric explanation for why you have equidistribution in one and not in the other. Now, let me move to the next plot. So this was the quantum side of the business, because I'm plotting eigenfunctions. I interpret them in a quantum mechanical way. Here's the classical side, which is the dynamics of the billiard ball flow. The usual flow, when you go in straight lines, then you bounce off the boundary. And you keep going. So here's a long trajectory of the billiard flow. On the left, the billiard flow on the disk is completely integrable. You have another conserved quantity. And on the right, this, On the right, it is what's known as ergodic. Namely, if you take a generic trajectory, almost every trajectory will equidistribute as time goes to infinity. I'm not going to write a formal definition, but you see that it looks like it's densely wrapping around, and the amount of time it spends in a set becomes proportional to the volume of the set. All right. And this ergodicity is due to Bunyamovich, which is why this is often called Bunyamovich stadium. Obviously, Bunyamovich did not invent the stadium shape. He proved that the billiard flow is ergodic. All right. So what I'm going to talk about today generally falls into a certain subfield of quantum chaos, where we want to say that if you have a system where the classical flow, here the billiard flow, has chaotic behavior, then there is equidistribution of eigenfunctions. Okay, so all the statements will be in this vein, except, well, life is not perfect, and so it gets more complicated, but that's what we're aiming for. Classical chaos implies quantum chaos. That's what I'm going to be talking about. And so let me start with an old result, which is called quantum ergodicity. It's, you could say it's the foundational result in this specific corner of quantum chaos. Namely, let's assume that my planar domain has ergodic billiard flow, as the way I defined before. Then most eigenfunctions equidistribute. So it's all great. You get equidistribution according to the volume measure. But the only caveat is that you cannot prove that all eigenfunctions equidistribute. Instead, you have a density 1 subsequence of the eigenvalues so that the corresponding eigenfunctions equidistribute. Kind of, if you do ergodic theory, it sort of makes sense, because most trajectories equidistribute, so most eigenfunctions equidistribute. And that's what you get. So this was done in the boundaryless case, which I'll talk about soon, by Schnirelman, Zeldich, and Coulon-de-Verdier. In the case with boundaries due to Gerard Leitzman, and the more general boundaries are due to Zeldich and Zworski. All right. And I should say that this theorem here, I stated it for planar domains because it's easy to draw. Right? Everybody understands what a planar domain can look like. But actually, it is often more convenient. It's a more general case, but it's also more convenient technically to study general Riemannian manifolds, with or without boundary. So this means that you can fix a metric on your manifold, which is not the Euclidean metric. You have a natural Laplace-Beltrami operator that generalizes the Laplacian. You still have a complete system of eigenfunctions. And then the billiard flow, the classical flow, would be replaced by geodesic flow, because if you had a quantum particle on a manifold, a Riemannian manifold, then geodesics, they would correspond to straight lines. And this kind of quantum classical correspondence that leads to this result tells you that your quantum particle localization should somehow propagate along whatever a straight line is. So in a Riemannian manifold, that would be a geodesic. All right, so this leaves only one little question. So as you can see, I'm almost done. Namely, do we have equidistribution for all eigenfunctions? All right, let's see. So we have the stadium, right? OK, here is more pictures, wonderful pictures by Alex Barnett. And so what do you think? See, most of them equidistribute. Of course, there is thousands of eigenfunctions, but I can't show you thousands of eigenfunctions on this screen. So you can just believe me that most eigenfunctions do equidistribute, consistent with quantum ergodicity. But some eigenfunctions don't. And there is actually a mathematical result to this effect due to Hassel. OK, right? So sometimes things don't equidistribute, and you see what's known as scars. So here, for example, this one is, of course, the worst on the picture, right? And you see a scar. You see a localization, which looks like it's localizing on this kind of bouncing ball modes, or on this bouncing ball orbits like that. OK. All right, so what do we do now? Well, one way to think about this is that the problem with the stadium is that it's chaotic in the sense that the geodesic flow is ergodic. Almost every trajectory equidistributes. But it's a weak chaotic property. And in particular, there are these trajectories bouncing up and down between the two straight ends of the stadium that might take a very long time to equidistribute. I mean, the ones going exactly straight never equidistribute. But if you go kind of by angle epsilon, it will take you time about 1/epsilon to enter the other domain. And so that's the problem. And so one way to fix this is to consider systems which are strongly chaotic. So they satisfy a stronger assumption, which is not satisfied by the stadium in particular, and try to postulate equidistribution for those. So now I'm going to completely embrace Riemannian manifolds. So I apologize, but here I have to make a switch. Boundaries are very annoying because of diffraction of the boundary. And so I'm going to assume that it's boundaryless compact Riemannian manifold. Okay. And we have the eigenfunctions of the Laplace-Beltrami operator. And here is a conjecture due to Rudnik and Sarnak. I remember talking to the late Steve Zeldich about this, and he said that of course, he thought that this conjecture, should be made, but he spent, instead of formulating in a paper, he spent a lot of time proving it. And that, unfortunately, did not succeed. It, so far, is quite open. But here's the conjecture. The conjecture is, let's assume that my metric has negative sectional curvature. Trust me until a few slides later that this is it gives you strongly chaotic properties of the geodesic flow. Okay, this might not sound intuitive at first, but that's the assumption that the flow is strongly chaotic. So it's a negatively curved manifold. Then the entire sequence of eigenfunctions equidistributes. So as I said, the conjecture is very much open, and it has informed a lot of works in quantum chaos, that some of which I'll present in a moment. But there are some cases in which it is known. In particular, is a notable case due to Lindenstrauss on certain arithmetic surfaces where you have additional symmetries that can help you out a lot. So there's a certain additional algebraic structure that you can sometimes exploit. But without such structure, there is not a single example where it is known. All right. So here's another picture. I'm not going to define it too much, so you don't have to look at those little numbers on the top and so on. But so this is due to Alex Strohmeyer. And what is plotted here is a hyperbolic surface. So I want a manifold of negative curvature. I forgot to say the dimension should be at least 2. Okay, for dimension 1, everything is very simple to figure out. So the simplest case would be you have a surface. And I said I want negative curvature, so the simplest case should be constant negative curvature. So you all know a surface of constant positive curvature, the sphere. hopefully also know the surface of constant zero curvature, the torus, doesn't embed into R3, but it's there. But there's also surfaces of constant negative curvature, which appear in many areas in mathematics. And that's the one that we'll be using here. And well, you can glue them. This is what's done there, if you look very carefully, is instruction to glue your hyperbolic surface from a hyperbolic 12-gon, I believe. Gluing sides together, you get a surface of genus 2. Okay, so surface with 2 holes. And here are our eigenfunctions. For reasons I don't completely understand, Alex chose orange as his 0 marker. And then, but you can see that it equidistributes numerically. And you plot all of those eigenfunctions, they all equidistribute. And the QE numerically seems to be definitely true for hyperbolic surfaces. Yet, nobody knows how to actually prove it, even for hyperbolic surfaces, which you could say is the simplest, cleanest case in some sense. All right, so now let me talk a bit about the geodesic flow on hyperbolic surfaces and why the negative curvature matters. Well, I'm going to cheat. I'm not going to write a formula where you start with negative curvature and get chaotic behavior. But what happens is this. So I'm going to study the geodesic flow. I have to be a bit more systematic here. The geodesic flow is not a flow on the surface, because in order to find out where you end up, you need to know not only where you started, but also which direction you were going, right? So the geodesic flow is a flow on the phase space of this classical mechanical system, if you want. And the phase space is the unit tangent bundle. So it's a set of point and the direction on the surface. Direction you can think of as a unit length vector. So this is a 3-dimensional compact manifold, because my surface was compact. And you have this geodesic flow on it. So for each point and direction, you give me a time t, then I'm going to flow for this time, and I get another point and direction. And so that's what the geodesic flow is. Now, it turns out that for hyperbolic surfaces, shockingly, the flow is hyperbolic. But it means a different thing. Hyperbolic surface means constant curvature -1. The flow is hyperbolic. I will give a special case of it, which is very neat and true for hyperbolic surfaces. Namely, you can decompose the tangent space to your phase space. So the space of infinitesimal deformations of geodesics, or geodesic initial data, which is 3-dimensional, you can decompose it into 3 directions. You can say there is a frame of 3 vector fields on this SM. There is a flow vector field. So if you change your geodesic along the flow vector field, well, it just shifts. Nothing interesting happens. But then there is a stable and unstable vector fields, which are exponentially contracted and exponentially expanded by the differential of the flow. So if you don't like thinking about differentials of flows, the common way to think about it is, imagine I have this geodesic. Imagine I lived on a hyperbolic surface, right? Now imagine that I change my, let's just say I change my angle slightly, right? So what happens? So I go sideways, right? And if this was epsilon, then I have a distance about epsilon t from where I used to be, right? From the original trajectory. But if I'm on a hyperbolic surface, more violent things can happen. Namely, if I take my initial geodesic and then I deform, it requires a deformation of both a position and a velocity vector along this unstable vector field. What's going to happen is I'm going to diverge from the original trajectory exponentially fast. And similarly, if I deform in the stable direction, then I will converge to the original trajectory exponentially fast. So that's something that's easy to check, because you have explicit formulas for everything here. But that's where negative curvature makes a huge difference, because you can see that, well, in all this chaos, I lost my clicker. Anybody seen my clicker? But it is a mystery. But in any case, oh, here it is. So the strongly chaotic behavior of the geodesic flow is a consequence of 3 distinct phenomena. Exponential contraction in the stable direction for the flow, exponential expansion in the unstable direction, and wrapping around the compact manifold. Because the manifold is compact, so you cannot expand exponentially far, or rather, you're going to wrap around and come back. And those 3 give us the chaotic behavior of the geodesic flow. Okay. All right. So instead of deliberating, instead of delving deeper into that, I'm going to give you a much simpler example of hyperbolic behavior, which is not a flow, it's a map on the torus, the so-called Arnold-Cat map. And this is just this. You take a torus, which is R2 quotient by Z2, and then you take a linear, you just take a linear transformation of R2 that preserves the Z2 lattice. So this just corresponds to an integer matrix, and here I'm going to take matrix 2, 1, 1, 1. So I just have my initial block here. Right? Imagine this was the torus. This is actually very convenient. Most rooms don't have this kind of tiles. So imagine I'm sitting in a tile in the torus, right? And then as I apply the transformation A, this square will be mapped to a parallelogram. But then I'm quotienting by Z2, so I should cut the pieces of the parallelogram and rearrange them. And what happens here is my A has eigenvalues, two eigenvalues. One is bigger than 1, and one is less than 1. And they're inverses of each other because it's volume preserving. And so you have this exponential expansion contraction along the eigenspaces. So here the eigenspaces are the unstable and stable spaces. There's no flow direction. This is a 2D thing. And then you wrap around the torus. And so this causes this chaotic behavior. So here's why it's called the Arnold-Cat map. The cat was, no cats were harmed in the making of this video. The picture of the cat and the cat itself is due to Jeffrey Golgowski. So you start with a cat. And then let's just apply pixel by pixel my transformation to it. You see here you can still kind of make what happens, right? You had a cat. And then you can imagine this is my parallelogram where it got stretched, and then it got recombined because I'm on the torus. Now I can do it more and more. You can see where's the stable and unstable direction, right? You can see this long streaks is the unstable eigenspace, and more, and more. And at some point, once I exceed the resolution, it'll just start looking like that. Okay? So this is a legitimate and easy to illustrate example of strongly chaotic behavior. All right, let's move on from the stretched cat. So that's what I wanted to say about the classical geodesic flow, or about this hyperbolic behavior. So you see, coming forward, we will always be assuming negative curvature, and the way we'll be using it is in the strongly chaotic property of the geodesic flow. That's the classical side of this. Now, before proceeding to the quantum side, I have to go through this somewhat tough to present slide. This slide hides about a semester-long course in semi-classical analysis. In fact, Professor Zworski wrote a book, which has other chapters too, but you would need, I don't know, 5 or 6 chapters of that book to really understand in technical detail these constructions. But I can explain in rough terms what happens here. And so I'm going to talk to you about micro-localization, which is localization in position and in frequency simultaneously. So previously, we only studied localization of our eigenfunctions in position. You see the integral on the top. We were studying those integrals, right? I fixed an observable A, and then I took integral A absolute value uj square. Now, quantum mechanically, instead of thinking of it as an integral, you should think of it as an inner product. A real quantum mechanics person would write the bracket notation, but I couldn't bring myself to do this to you. So this is really multiplication by A applied to uj, and then inner product with uj, same thing, right? And then we're studying the limits of that. Now what we want is we want to expand the possible observables that we can apply to our eigenfunctions. And the way we do it is we use what's known as semi-classical quantization. So this is a bit much to absorb, and then there will be some pictures later to try to make it more palatable. But roughly speaking, you can start with a classical observable, which is now a function on the cotangent bundle. There is a reason why co, but let's not talk about that here. And then this classical observable, you think of it as function of position and momentum. So you think of the x coordinates. So it's a function of 4 variables locally on my surface. The first 2 variables are the position variables x. The other 2 variables, their classical mechanical interpretation is the momentum of the particle, not velocity, momentum. And then it turns out that you can quantize it. You can quantize it to a family of operators on L2 of your manifold. And formally, it looks like you take the momentum variables and you replace them by minus IH times differentiation. Minus I makes sense because that makes real things self-adjoint. H I'll have to explain. And of course, algebraically, this makes no sense because x and partial x do not commute. So there is a lot of work that needs to be done, which I will not do today. And then we have this mysterious animal, which is a family of operators depending on H. And then I'm going to apply it to my eigenfunction and take the inner product with itself. And so these will be my quantum observables that I want to study. And in fact, this is what they would do in quantum mechanics, except they would call this op H of a hat. And what it tells you, it tells you the expected value of the observable A of position and momentum. So it lets you access not only the position of your quantum particle, but also the momentum of the quantum particle. All right. And then my Hj here will be lambda j inverse. If somebody else, I can explain in detail. But roughly speaking, this has to do with the fact that my eigenfunctions will be oscillating at a frequency which is about square root of the eigenvalue. So that normalization normalizes it correctly. It matches what you see with concentration of eigenfunctions with how fast they oscillate. OK, so we'll study this kind of objects, and we'll study their limits. Now, the previous limit, localization position, is a special case. Because if your A is a function of the x variable only, then for typical choice of quantization, op H of A will just be the multiplication operator by A. And we're just back where we started. But what you can also do is imagine that my manifold was Rn. Otherwise, I have to choose coordinates and start talking about more things. If you had a function only of the xi variables, of the momentum variables, then this mysterious quantization operator is a Fourier multiplier. So it lets you access localization in the Fourier space as well. You have to think carefully about this. You have to think about taking your function, cutting it off, putting it in coordinates, looking at the Fourier transform, and see in which directions the Fourier transform is big. But that's what it would encode, say, if you did it numerically. And you see that the relation between frequency and momentum is like this. A frequency is momentum divided by h. So if momentum is around 1, it means I'm studying my function at frequency about h inverse. Okay, so there is this frequency rescaling that always has to be there. Again, it corresponds naturally to the fact that eigenfunctions oscillate at frequency about 1 over h. All right, so we're through that slide one way or another. And now I can deliver on more fine way to study macroscopic localization of eigenfunctions in the high energy limit. And so this brings me to the concept of semiclassical measures. So I would say that a sequence of eigenfunctions converges semiclassically or microlocally to a measure mu on the cotangent bundle if you have the following limiting statement. So on the left-hand side is this quantum observable applied to uj. So that's what was defined on the previous slide. And on the right-hand side, well, the limit will be h independent, and it's the integral of a with respect to this measure mu. Okay? So one thing to note is that if I only take a's which depend on x, then the left-hand side is just integral a times absolute value j square. And then looking at this statement, you can see that absolute value uj square dx will converge as probability measure to the push forward of that measure on the cotangent bundle. Okay? So it gives you more information. You can project it to the base, and you just get usual localization of absolute value u square. But if you don't project that, again, you access more information in which directions it oscillates, or in which directions is the Fourier transform big. So I will say that a measure is semiclassical measure if it appears as a weak limit of some sequence of eigenfunctions. Okay. So here, there is a certain compactness here. You have this big zoo of eigenfunctions, and they can localize in different ways. But there is an analog of Helly's compactness theorem here that tells you that you can characterize how they localize by all possible subsequential weak limits. So any sequence of eigenfunctions, you can find a subsequence which will converge to one of those. So it's a topic present in many areas of mathematics where you study the limiting object to understand the localization of the actual eigenfunctions better. All right. So it's a more complicated object to define, this semiclassical measure. But there is a big payoff because it has some nice properties that the original projected thing does not. Well, it's a probability measure. Just take A equals 1. It corresponds to normalization of the eigenfunction. The support is contained in the unit cotangent bundle, and that corresponds to the fact that eigenfunctions oscillate frequency lambda j. But the third property is the really nice one. This measure is invariant under the geodesic flow. And that's not something you can access in the base because there is no natural flow in the base. So this brings us into realm of ergodic theory. So somehow you start with sequence of eigenfunctions, some quantum question, and then you get to this limiting object, which has invariance under the geodesic flow. And what we'll do is we'll study those. Okay. All right, let's do this. So I'm getting ready to state the main results, which is great. So first of all, I want to upgrade my equidistribution property. Previously, I wanted equidistribution position. Now I want equidistribution position and momentum. And we can translate it to saying that the microlocal limit is, of my eigenfunctions is the Liouville measure, which is just a natural volume measure on my manifold. So it means it equidistributes in position, but it also equidistributes, by angle in frequency. So that's a stronger statement than localization, because if you project this Liouville measure, you just get the usual volume measure. And then the statements I gave before, quantum ergodicity and quantum ergodicity, actually feature this microlocal version of it. Sometimes these are called microlocal lifts of the limiting measures. Now, the good news is we have this phi t invariance. The bad news is there's lots of flow invariant measures on a SM. There is the Liouville measure, but you can also take any closed geodesics, of which there are plenty, take a delta measure on that, that's flow invariant. And so the properties on the previous slide do not narrow down much what kind of semi-classical measures you can get. And so that's where I'm going now. So QE conjecture is that the Liouville measure is the only semi-classical measure. This is not something we can prove, but instead I can present two results which give you restrictions on what measures can appear as semi-classical measures. So there's a restriction on how localized your eigenfunctions can be in the high energy limit. Okay. All right, so these statements here, they will have the form that the eigenfunction is somewhat delocalized, but not absolutely equidistributed. Okay, so I'll start with a later result because it's easier to state. And here is the result. So I'm on a negatively curved surface. Hyperbolic surface is a special case of that. Then the every semi-classical measure has full support. Wait, that's the statement. What it means is that the measure is positive on any non-empty open set. So in particular, what it tells you, if you don't like these limiting objects and semi-classical measures in ergodic theory, there's a theorem you can state here, which doesn't feature any of that. Take a negatively curved surface, fix a non-empty open set just in the surface, in the base. Then you have a lower bound on the volume, or on the L2 mass of Laplacian eigenfunctions on this fixed macroscopic set, which doesn't depend on the frequency. So as your eigenvalue goes to infinity, this lower bound doesn't degenerate. So the probability of finding your quantum particle in a set is separated away from 0. Quantum mean ergodicity will tell you that this probability becomes proportional to the volume, which is, of course, a stronger statement because the volume of any non-empty open set is positive. All right. So I'll flash here. This is only known in dimension 2, but there's various progress towards making it work in more general cases in higher dimensions, but I don't think I'll talk about those works in detail. OK, so that's one result. And so it tells you that your semi-classical measures are somewhat delocalized. They have to have full support. So for example, delta measure on a closed trajectory is out, because that doesn't have full support. So you cannot scar that strongly. But this is not the first time, actually, somebody proved that a delta measure on a closed trajectory cannot appear as this limit of sequence of eigenfunctions. You cannot have such strong scars. The first time it was done, it's following from various entropy bounds. And so that's a different way of saying that your eigenfunctions or your semi-classical measures are delocalized. So it would be great to have quantum mean ergodicity. It would make all of those theorems obsolete. But we don't have that. But instead, we have not one, but two different ways to say that semi-classical measures have to be delocalized. So the simplest theorem to state here, which I do in hyperbolic surface, is that the entropy of each measure has to be at least 1/2. I have a slide in a moment where I explain what the entropy is. In general, it holds actually on any negatively curved manifold. You don't need the dimension, you don't need constant curvature, but the constant is harder to write down. So I'll stick to this one. So I should say, before I define entropy, the Liouville measure in this setting has entropy 1. The delta measure has entropy 0, so that's why it's excluded. And here you say the entropy is at least 1/2, so you excluded half of possible semi-classical measures. Of course, it's nonsense because it's a big infinite set, so what do I mean by half? But you get halfway there. If you prove the entropy is at least 1, that's quantum unique ergodicity, because the only measure of that entropy would be the Liouville measure. But this half is actually an important threshold because there is a toy model case of quantum cat maps. Like the cat maps I showed, you can quantize them. I'm not going to go into detail. But in this setting, you actually have a counterexample to quantum unique ergodicity by Fornon and Masher and DB-Ever. And what they did is they constructed a situation where you have a semi-classical measure that looks like half a delta function plus half the Liouville measure. So you have a half-weight scar on your measure, and that has entropy exactly 1/2. OK, right? So as I said in the beginning, it's a bit more complicated. I wish I had a proof of QE for you, and then we can, But OK. OK, what's the definition of entropy? I'll do it by picture. And I'll use the cat map model because it's much easier to visualize than the 3-dimensional sphere bundle of a hyperbolic manifold. So I start with a fixed fine partition of my phase space. Here I just have 4 quadrants. Then I'm going to refine it using here I use the cat map, but there I would refine it using the flow, which means that I keep track not only on which set of the partition I'm at, but also which set of the partition I was at time 1, 2, and so on until n. Okay? So you can see this is 2, so I keep kind of 2 pieces of information. You can think of just taking this partition, applying your A to it, and then just drawing all these things, and you get these finer sets. And now what you do is the following. You see you have a lot of sets. So here I'll show it here. See you have a lot of small sets there. Now you have a measure mu. Take a mu random point on this phase space. It lies in one element of the partition, of the refined partition. Look at the measure of this element of the partition. Then the expected value of the log of that measure will grow like minus the entropy times n. So the way you should think about it is, OK, some of those sets could be very small. A lot of them are empty, actually. If you really think about it, set theoretical, a lot of them are empty. But if you take a generic one with respect to the measure itself, it will have measure approximately e to the minus number of steps times the entropy. And that's the way to think about entropy. Right? So that's this number that is associated to your measure. All right. Now, how many minutes do I have? 15. That's a lot. Wow, well, you're in for a treat. Does anybody have any questions about entropy? Maybe I'll tell you first a few fun things about entropy. Look, so here's how I can compute the entropy. Nobody in their right mind would do this and actually tell you how to compute the entropy in a general math audience talk. But on this picture, I can do it. Let's start with entropy of the delta measure. Pick a point that's random with respect to the delta measure. Well, it's deterministic. Let's say it's in the middle. It lies in exactly one element of the partition. And the measure of this element is 1. You just don't see, from a point of view of delta measure, you just don't see anything except one element of the partition. And so you get entropy 0, because log of 1 is 0. Right? There's no growth. Now, if you took the volume measure instead, what happens is, imagine lambda is the eigenvalue of the matrix A that's bigger than 1. Then you can see that those things look kind of like rectangles, those refined ones. And they look like rectangles. I'm looking at this picture. Oh, sorry. Press the wrong button again. I'm looking at this picture. If you look at those sets, they sort of look like tiny rectangles. And they're in the unstable direction, it's length 1. And in stable direction, length lambda to the minus n, because you shrink by lambda every time. So you take an arbitrary one. Well, its volume will be about lambda to the minus n, right? Product of width times height. And you take the log of that, and you will see that the Kolmogorov-Sine entropy will be minus log of the eigenvalue. And geodesic flow has expansion rate exactly 1, which is where I get entropy 1. How about that? Okay, well now let me tell you a little bit about the proofs. So I'll discuss those proofs briefly. I have some slides tucked away at the end in case I run really long on time or somebody asks a question. But here is a kind of big picture of how we do it, or how we and how people prove these theorems. So remember, we have two theorems now. One says that the semi-classical measure always has full support. The other one says it has entropy at least 1/2. Theorem 2 and theorem 3. Information about semi-classical measures is macroscopic information because it's obtained by fixing an H-independent or lambda-independent observable and letting eigenvalue lambda go to infinity. So you have to start with this macroscopic information because that's ultimately what the statement of the theorem features. And you have to refine it somehow. You have to relate it to microscopic information, which is localization, micro-localization in sets which depend on the frequency. This is hard. It was, the first time it was figured out in this context was in Nalinian and Taraman's 2007 paper, and it's rather complicated, but by now people have an idea how to do this. And this uses the fact that micro-localization of Laplace eigenfunctions is invariant under the geodesic flow. So the measure is invariant, but this finer localization is also invariant under the geodesic flow. So you can refine your crude localization to somehow fine one. And then, once you do step 2, you see that if your semi-classical measure violates the conclusions of theorem 2 or 3, if it's too concentrated, then the fine micro-localization you get in position frequency is inconsistent with some kind of uncertainty principle. Maybe that's not how it was formulated in the original paper on Taraman, but you can certainly interpret it this way. So here I'll give you an example of micro-localization versus semi-classical measure. 3 functions. You don't have to bother about the formulas, especially things in gray. I just don't want my math to be wrong on the slide. So I start with this. It's a Gaussian of width h. That's what it is. Gaussian just because, easier to write the Fourier transform. Okay? So this Gaussian function, it is micro-localized at position about h, right? You can see it lives in h interval. It's not 0 outside, but it's very small outside of that interval. But if you think about frequency, it lives on frequencies up to h inverse. The Fourier transform of that, if you compute it, lives on an h inverse sized interval. And so momentum, however, is not frequency, it's frequency times h. So in this quantum mechanical picture, it's micro-localized roughly on this rectangle. H in position, 1 in momentum, which is h times frequency. Okay. And the semi-classical measure, if you compute it, it's a Gaussian prefactor times delta function in x and the Lebesgue measure in psi. Psi is the momentum. So it looks like it lives at position 0 and all momenta. Okay, it's delta function on a vertical line. Okay, here is maybe the most natural Gaussian, which is with square root of h. And when you do this operation, you'll see it lives in square root of h size interval in position and square root of h size interval in momentum. Okay, well, I can make it even bigger. So now I can just take an h-independent function. So it's slowly oscillating from our point of view. And you will see that it lives at position around 1. Again, the Gaussian is not supporting -1, 1, but it falls off pretty fast. And it lives in momentum around h, because it lives at about unit frequency, and momentum is h times frequency. So you get this red rectangle. You see, I forgot to say, I'm sorry. I know I'm not supposed to do it. For the Gaussian, this semi-classical measure is just a point. It's the delta function at 0. And it doesn't tell you anything. It's as concentrated as it can be from the macroscopic point of view. But microscopically, you can extract more information out of it. And here, the semi-classical measures on the horizontal line. So 0 frequency and all the positions. All right. So here is the most basic uncertainty principle. If you work really hard, you can use this uncertainty principle to show that you cannot have a semi-classical measure localized on a single closed trajectory. Single closed geodesic. And it's the following. Imagine you have a function L2 of r, and imagine it's micro-localized, whatever that means. It's small outside of an interval of size delta x in position, and you also know that in momentum, so h times frequency, it's localized in an interval of size delta xi. Then delta x times delta xi is at least h, right? That formula, well, might be familiar to many of you. That's how it's usually stated in quantum mechanics. Of course, the devil is in the details what I mean by localization. I'm not going to go into that. So there's 50 different uncertainty principles as mathematical statements. And you see that those three functions, they all satisfy this. See, you can have a lot of localization in position. You can have h localization position, but then your momentum localization will be like 1. Or you can have a lot of delocalization momentum. You can have something oscillating in bounded frequency, but then it will necessarily be localized in an interval of size at least 1. And the Gaussian is square root and square root of h. So they all satisfy this. What you cannot do is you cannot have a function that's localized in an h-sized interval in position and also in an h-sized interval in momentum. Because then this function would be localized to unit frequency, but then it's slowly oscillating, so it cannot just be supported on a tiny interval. That's roughly why this is true. All right. OK, so now I'll spend a couple minutes on each of the theorems. So this was the basic uncertainty principle. Now I have to talk about upgraded uncertainty principles in very vague terms, say how they relate to the two theorems that I stated before. I start with theorem 2, which was the full support property. So theorem 2 said that my measure, semi-classical measure, has full support, which means that the probability of finding my quantum particle in any macroscopic set in position frequency is bounded away from 0, right? The measure is positive on any non-empty open set. Let's argue by contradiction. Let's assume that we found in an empty open set a small ball, right, on which this measure is 0, so my eigenfunction is micro-localized away from this ball. Now here's the part where I have more details, but unless somebody presses me, I'm not going to write more notation. I'll just be more vague here. If my function is micro-localized away from the ball, because micro-localization is invariant under the geodesic flow, which again is a statement that one has to prove. It's called Yegorov's theorem. That's one way to do it. My function also has to be localized away from the images of this open set under the flow. And so let's look at those images. So I use again the cat map because it's easier to plot. So imagine my hole, my set U, was the white ball in the middle. So if I don't use anything, I know just that my eigenfunction is localized in the black set, micro-localized in the black set. Here, horizontal is position, vertical is frequency. OK, if I refine it for positive or negative times, I'm going to get localization to those sets. Right? I'm using invariance under the map. So those new ellipses are just the images of the original hole under the cat map. So yeah. Well, I can continue this. And you see things get finer and finer. And maybe here I stop with this illustration because it gets below the resolution. But you see that once you use this to its extreme and you go for t up to log 1 over h, this means that the thickness of those streaks will be about h on a hyperbolic surface, because like e to the minus t. You see that your function has to actually localize to the set on the left and to the set on the right. And then if you turn your head, it kind of looks like localization to position and frequency on a fractal set. And there is a tool called fractal uncertainty principle, due to myself and Bourgain, that tells you that this is impossible. So that's how you prove the theorem in very vague terms. All right, well, how do we do the entropy? Here I'm going to be even more vague. That I still have 5 minutes? Wow. OK. I don't know what went wrong there. I usually run over, but OK. I'll take it. So you have the, so how do you prove the entropy bound? Even though it was a much earlier result, like 10 years before theorem 2, it's sometimes a bit harder to explain. But the main tool is another kind of uncertainty principle, which here I state in a primitive form. You need a more advanced form of that. But here's what's known as Hirschman's uncertainty principle. Take a function in L2 of R of norm 1. So think this is my quantum wave function. And then I'm going to define something called the Shannon entropy, which is that expression with logs. If you remember how I defined entropy before, it's sort of absolute value f square is a probability distribution. You take a random point with respect to absolute value f square, and then take minus log of absolute value f squared and take the expected value, right? That's what this integral is. So it is a sort of entropy. And then if I fudge my Fourier transform bit so that I don't have to worry what the constant is, the entropy of absolute value of square and the entropy of absolute value f hat square, the Fourier transform, is non-negative. The sum of those two entropies is non-negative. What this means is that imagine your f was very localized. If your f is very localized, that looks like the delta function, and it might have a large, I guess, negative entropy in this setting. But then the Fourier transform will be delocalized, and it would have to have a large positive entropy, and they'll have to cancel each other out. You can actually do it instead of 0. I think you can do it log e over 2, and then it's sharp because the Gaussian exactly matches that. But for us, it doesn't matter what the constant is there, right? And so now when you look at your eigenfunction u, you write it microscopically, like, I'm sorry, I'm going to do this again, even though it's a different theorem. But you see how here you see sort of rectangles in the unstable direction, rectangles in the stable direction appearing in the phase space. So we use those rectangles, and we find a basis of L2 of our manifold, which is, which there is an unstable packet basis and a stable packet basis. And the properties are the following. You can think of writing your function as a superposition of unstable packets or as a superposition of stable packets. It turns out because of the flow invariance, the coefficients that you get, you should think of them as functions in L2 of R. You can think of these packets as you just move along one direction, so it gives you a real valued function as coefficient. Turns out that the entropies, these entropies here of those two coefficient functions, so the coefficients in the stable basis or the unstable basis, they are related to each other. They're roughly equal, and they're also related to the entropy of the actual semiclassical measure. This is macroscopic to microscopic. And then, but if you have a space with two bases, this means you can write one basis in terms of the other basis. So there is a relation between those coefficients in the stable and unstable basis. I should say I learned that specific way to present it from Alex Cohen. And so the way those are related, roughly speaking, the unstable coefficients are the Fourier transform of the stable coefficients with a certain rescaling. And so you know that your entropy is of VU and VU hat is the same. And you also know that the sum of the entropies is bounded below. And this gives you the correct bound on the entropy of the original measure. So there's a lot of details missing. I don't explain why 1/2, but roughly speaking, if this 0 was 1, then you have entropy of this plus entropy of that is at least 1. And then, but they are equal, so this means it's at least 1/2. It's a very crude explanation, but that's, I think, best I can do. And that's it. Thank you for your attention. Concluding remarks? Okay. So what have we learned?
I was told I was supposed to ask if there are any questions for the speaker, and one ought to use those microphones if one has questions. Oh, please.
Why that is useful? Yes. Or here you mean? Yes. So why does this quantity? Oh, that's interesting. Sorry, something happened. It got desynced. The ladies and gentlemen in the back, would you please synchronize my computer? Thank you. Yeah. Okay. There you go. Here's the Shannon entropy. Well, why is it useful? Several reasons why. So A, it has a certain self-similarity property under refinement. If you took your measure and you somehow refined it several times, and the measure was invariant under some flow, then the entropy of the refinement would be n times the entropy of the original thing. It's hard to see in this particular definition, because what am I refining under? But That's one reason. So it lets you relate the macroscopic information, the entropy of a partition for the original semi-classical measure, to microscopic information, because you can refine your partition sets under the flow and get to tiny rectangles of size about h, and that's where the uncertainty principle starts kicking in. Secondly, it has this uncertainty principle that we can exploit. So you can see that the entropy has a lot of nice properties, and you can see that you have two functions. One is essentially the Fourier transform of the other. I'm lying in several ways here, but essentially for this purpose is the Fourier transform of the other. And so if the sum of the entropes is bounded below, then at least one of the entropies has to be bounded below, but they have the same entropy, and it's related to the original number we want. So it turns out very useful. I mean, if really need, I can forward your question to Professor Hasselblad, from whose book with Anatol Katok I learned about entropy, but that's one take on why entropy is useful. It's a common thing to use in dynamical systems. Yeah. Oh, Lior? Yeah, that's pretty tall. I don't think you're small. I think it's just really tall. I don't think. I don't know. So the question is, what can be done if we don't make the strongly chaotic assumption? And that is hard. So the best thing we usually have is quantum ergodicity, which I stated in the beginning, because ergodicity is like outside of a measure zero set statement, and that statement can only get you most eigenfunctions, which is already really good. Many people would settle for just most eigenfunctions, but we can't just be reproving quantum ergodicity every year. So if you want all, then you need uniform properties, and that gets very tough. As an example, we don't know how to do theorem 2, the support property, in higher dimensions. And for some specific cases, Alex Cohen's new fractal uncertainty principle is actually helping with that a lot. So that's one of the big pieces of the puzzle it's solved. But there's a lot of other things that happen in higher dimensions, even for uniformly hyperbolic systems. So I guess we're not done with uniformly hyperbolic systems yet.